I'd like to thank the organizers for inviting me to speak here today. And I'll be talking about these two papers written in collaboration with Tim, Andrea, and Anton, who are all in the audience still. So, and I'll be talking about some on-shell approaches to cell force. Okay, so you've probably seen a slide like this about 100 times already in this workshop, but I'll go through it again. So the two-body problem, I would say, is still one of the outstanding challenges of GR today. And it has received a lot of recent attention due to the observations by LIGO and this new kind of field of gravitational wave astronomy. And with the upcoming new observatory like LISA, we'll be able to measure many new types of events. So I have this plot here of some the characteristic strain produced at various frequencies from various types of events. And then we have these sensitivity curves of the observatories that exist, or will exist at some point. So for pulsar timing arrays, we can measure the stochastic background. And with LIGO, we were able to measure compact binary inspirals. And then with LISA, we'll be able to measure things like the extreme mass ratio inspirals and positive binary mergers, essentially. Yeah, and anything above these curves we'll be able to measure. Okay. And I think Victor already talked about some of this yesterday as well. So in order to measure these, we also need some results to compare against. And these, if you're talking about laser interferometers, we have to measure the strain felt by the arms as the gravitational wave passes in space. And in calculation, this usually corresponds to the waveform of the gravitational radiation that is felt. And there are many ways to approach calculating this kind of thing. So, for example, numerical GR or analytical GR or effective one-body problems. And we've seen already some summaries of these things by Tanya and Victor. And I just want to highlight that extreme mass ratio inspirals, we're actually expecting very many events like this to be occurring during the measurement period of LISA. And the gravitational cell force is a very natural way to look at approaching the calculation of the waveform for these extreme mass ratio inspirals. So this is a sketch of basically what happens here. So in this case, we have a very small mass ratio between the two bodies. So we have a very large black hole and a very small body. So let me go into a bit more detail about this. So thankfully, Victor already talked about this yesterday. But if you weren't there, in the cell force expansion, we expand in the mass ratio. So here's epsilon, and which is equal to the small mass over some v, which is the mass scale of the a mass scale associated with the background. So for a black hole would be the mass of the black hole. And we expand basically everything in this parameter. So for example, for the metric, we have the blue one here being the full metric. And then we can expand it in a perturbation series around some background metric. And in the same way, it's possible to expand the stress energy tensor in moving in the full metric in a perturbation series just like this. And in this case, the first order term will just be the stress energy tensor of a point mass moving in the background G mu nu. So that means that at leading order in the cell force for radiation, so for this H1 mu nu, we simply solve the usual linearized Einstein equations on the background G mu nu for a point mass. And at higher orders, things get a lot more difficult. And we see the failure of the point particle approximation for the small body. And that means that the equations become too singular to be integrated. And so we need to use more advanced methods, such as dividing our background and dividing our perturbation into regular and singular fields, using some matching conditions around the small body, and so on. So there's a nice review by Barrack and Pound from 2018. And again, Victor already discussed it, so thank you. Okay, so that's kind of the cell force. But maybe the reason that most of us are here is because there's been a new approach to two-body mechanics using the post-Minkowski expansion from like amplitudes in QFT. So this means that we can calculate classical quantities such as the gravitational potential, waveforms, the impulse, and so on, expanding in the weak gravitational coupling. So, so there are some very impressive calculations from some years ago now as well. And the KMRC formalism makes it easy to get, or easy, but we can express classical observables in terms of the classical limit of quantities built from these amplitudes. So this is just a sketch of, for example, what the impulse would correspond to. And Ingrid, I don't know if Ingrid is here.
He's left.
Okay, Ingrid also mentioned it. Okay, right. So this is maybe a controversial slide, but what are some advantages and disadvantages of using amplitudes? So for one, like QFT amplitudes is a very like old field, I think, at this point. So there are a lot of powerful ways of evaluating Feynman diagrams, so, such as like generalized unitarity and things like that. And it's also possible to build gravitational amplitudes from simpler ones using double copy, such as BCJ for loops. But some of the disadvantages are that, or in my opinion, are that the expansion in the gravitational constant is not really a natural way to look at like geodesic motion, for example, which is nonlinear in the coupling. But there's always asterisks to this. So in this paper, that was shown some very like powerful agreement between the cell force expansion and the PM expansion. And additionally, we're looking at scattering amplitudes. So usually you assume scattering events. But of course, the asterisk is that in Ricardo's talk, we looked at some ways of going to bound orbits. And before I move on, I just want to mention this recent like related work, which covers a similar approach to what I will be talking about as well, using more like EFT methods. Okay, but now let's look at another way of looking at this. So recall that what I was saying for EMRIs is that it's very natural to consider the Einstein equations solved on the background metric. So instead of looking at flat space amplitudes, so two massive particles scattering in some way and emitting some radiation, what happens if we look at calculations of one particle scattering on a big background, a strong background? So as we saw in Anton's lectures, at the start of this week, we'll define these using the perturbedness scheme. And in the classical limit, these particles are going to follow some geodesics on the background. And we can expect some properties of flat space amplitudes to still hold for these amplitudes on backgrounds. So for example, the double copy and some analytical properties. And also Sylvia talked about these things also holding for ADS and DS in the self-dual sector. And last of all, I think it's a natural way to approach looking at self-force observables. So for a lot of this talk, I'm going to talk about gravitational plane waves. I just wanted to motivate why I'm doing this and not just going straight to black holes. So this is the metric for a gravitational plane wave. And as you can see, we're in light front coordinates. And we have one non-trivial bit of the metric here in the dx minus squared direction. And one reason that these spacetimes are interesting is because of something called the Penrose limit, which says that any spacetime looks like a plane wave when viewed in a certain limit from along a null geodesic. So here, if you're an observer and you start traveling, start kind of approaching a null geodesic in a certain limit, like rescaling your clock and everything, then what you'll observe is something that looks like a gravitational plane wave. So for example, if we look at Schwarzschild, if you travel along a null geodesic with, or like start approaching a null geodesic with some radial component Rx minus, then what you'll start seeing is a spacetime that looks like this, where the L is the like conserved angular momentum from the null geodesic. And well, okay, I'm going to consider a further simplification in a lot of this talk, which is that I'll be considering actually sandwich plane waves, just because it makes defining the scattering states easier. So sandwich plane waves are defined by saying that you have Minkowski spacetime, then you have some plane wave, and then you have another Minkowski spacetime, so that you can define your asymptotic states. So the plane wave turns on and then turns off at some finite times, or like x minus. Okay. Are there any questions about this? Okay. So that brings me to the rest of the talk. So I'll be talking about ways to look at KMOC in curved spacetimes. And then I'm going to talk about some features of amplitudes on these plane wave backgrounds, which Anton has already kind of done. And then I'm going to present to you some of the waveform calculations that we've done. And then I'm going to just quickly go through some of the ways that it changes for black holes, like on Schwarzschild. So what happens on flat space for KMOC? So in gravity, we're interested in the leading 1/r term of the expectation value of the Riemann tensor at some point at null infinity. So that's what we're measuring. And this is defined like this. And we can compute this by taking the appropriate limit of some product of scattering amplitudes. And this is kind of like a schematic picture of the kind of things you need to calculate. So you have some, you have some Schell integrals here and some like waveforms, well, yeah, the shape of the wave and stuff like that. And then you take the appropriate h bar, goes to zero limit, rescaling all of your null momenta and things like that. Okay, and this is like the calculation that Ingrid presented. And of note is that the leading order term corresponds to a 5-point amplitude, or like a tree level 5-point amplitude on flat space. And in curved spacetimes, or at least in the spacetimes I'm considering, we instead, well, equivalently, we can calculate this kind of thing where we just, so doing some manipulations, it corresponds to this, where we have a product of a 3-point and a 2-point on the background. So we're now treating the background as basically one of these particles. And all of these quantities are evaluated with the like background dressed wave functions. And then we also have to send h bar. So in order to define these 3 points, 2 points on backgrounds, we also need to look at some further aspects of these gravitational plane waves. So this is the metric I was presenting earlier. And this can be rewritten in some other coordinates called Einstein-Rosen coordinates using the Kuhlbein. You just shifts your transverse coordinates to this. And we also make use of the deformation tensor sigma AB. So this, in a sense, describes how like certain null congruences after traveling through this plane wave, how they deform, like the shear and the expansion of this null congruence. Okay, so these are just some quantities you need to have in order to define the states on gravitational plane waves. So usually you start with, like in flat space, you just have e to the ik dot x as something you throw in. But on plane wave backgrounds, these things get dressed by the background, and you get all of these quantities, which are geometric quantities in the background. Okay. And we now have like an associated dress momentum that we're gonna throw into all of our calculations. And for metric fluctuations, it's a really nice property of gravitational plane wave backgrounds that we have something called a spin raising operator. So this means that we can just, instead of doing any calculations really, we can just apply spin raising operators to the scalar wave function. And this will give us our like spin 1, spin 2 states on these backgrounds. So here we have like this dressed graviton polarization vector constructed using this method. Okay, and then we throw all of this into our 3-point using the perturbiner method. And for example, here we calculated from the cubic part of the Einstein-Hilbert action. And then the final amplitude is going to depend on whether we're looking at ingoing or some outgoing states. So in what we're looking at, it would be an ingoing massive scalar of some kind, of some mass, and then an outgoing massive scalar and some emitted outgoing graviton. This kind of corresponds to this. And as you can see, everything, well, there are some things that stay the same due to symmetry. So we have this momentum conserving delta function in 3 directions. So in the plus and the transverse direction in 4D. But we don't have momentum conservation in the y minus direction or x minus direction. And this is because we don't have translation invariance, translation symmetry. And whilst this kind of looks like what we have for 3 points in flat space, all of these quantities are going to be dressed. And this is like the exponential of the Volkov exponent, which I tend to view as like a kind of spread out delta function in the y minus direction. So this is kind of a simplified version, but essentially you're like it's an exponential of the momenta in the minus direction. Okay, so this is our 3-point, and now we just go through the whole waveform calculation in this slide, or like between these 2 slides, and take h bar goes to 0, and we end up with this expression here. So yeah, this is just, I'm just showing this. So as you can see, here we have some geodesic dependence. So this is the geodesic motion of the scalar particle, I think. And we have some things that look like stress energy tensors a little bit. So we've divided these into 2 terms, depending on how like the differential acts on them. And for example, this T1 term just depends on these background dependent terms, sigma AB. Okay, and I'm using a picture. So for example, usually these calculations are very hard to do for general plane waves, especially in gravity. It's a bit easier in like electromagnetism. But for an impulsive plane wave, the metric becomes like this. We have now a delta function support. And then we can explicitly calculate the waveform that we get from this formalism. And it looks like this. What I've hidden here is that there's actually also a delta function at this 0 coordinate, which comes from just differentiating this absolute value here. But yeah, that's that. And that's kind of the end of the plane section. I'll now move on to kind of what we've done on Schwarzschild and how far we can go in this calculation at the moment. So what about black holes? The solutions to the 3 equations of motion are much more complicated than what I just showed in plane waves. For example, for the graviton perturbations, like we have to use the Reggie-Wheeler-Zerilli solutions, and for massive scalars, it's like the Hoyne functions, so confluent hypergeometric functions. And so to make our lives a bit easier, we make a WKB ansatz instead of using these functions. So we solve the Klein-Gordon equation on the background. So this is Schwarzschild. And then in the classical limit, we just solve the Hamilton-Jacobi equation for the background like this. And for example, in linearized Schwarzschild to first order in G, this is the solution that we get. And now in order to get the right actual like asymptotic behavior of the solution, we make like a weighted integral here in order to like get the right geodesic motion, matching onto the actual solution at R going to infinity. So this is so that we can kind of reconstruct using simpler objects, the actual solutions. And then the graviton can be constructed similarly. The one subtlety here is that we don't actually have an H bar in our equation of motion anymore, but we kind of make this ansatz to make it look like kind of dressed regularization inspired by the plane waves case. So we can then solve this. So we did this like order by order in G actually, and then match this onto the correct asymptotics again. So you can match it onto Reggie Wheeler-Zerilli in the Lorentz gauge, for example, if you're very enthusiastic about this. And then once again, we throw it into the cubic part of the Einstein-Hilbert action, and we get this expression for the 3-point, where again we have some like dressed versions of all of the flat space quantities. The complicated thing is that we have these weird matching functions, but okay. Okay. And then you can see that if you take the appropriate like classical and weak field limits of this expression, and also neglect the recoil of the background, so the big black hole, then this reproduces the usual 5-point that we have for two massive scalars emitting graviton at tree level. And then from this, you can throw this into the waveform calculation, like I showed earlier. And if you have enough computational power, then you should be able to calculate the waveform. And I would say it's very possible to push these calculations much further. So, for example, I mean, these WKB approximations, you don't have to do them. You can just use the actual solutions if you want. And you also don't need to linearize in the background like we did here. So that's kind of all I wanted to say. So the conclusion is that amplitudes on backgrounds can be used to calculate classical observables on these backgrounds. And this is, I would say, a natural way to calculate or to like start looking at calculations for the self-force approximation using on-shell data. And it would be really interesting to look at like further properties of these amplitudes on backgrounds, so especially on Schwarzschild. Like, is there a double copy there for these amplitudes, for example? And also to make it more concrete what the connection to self-force is with these amplitudes. And that's it. So thank you for listening, everyone.